Okay, thank you. Thank you very much for the introduction. Good morning, everyone. Welcome to the first lecture this day. So I will tell you some basics about calculating solid systems. Just briefly remind you what you have heard so far. So after some approximations that are accurate in many interesting cases like Born-Oppenheimer and approximate relativistic treatment, also approximations to exchange correlation functional in Kohn-Sham density functional theory, we convert the problem, very complex problem of solving the many electron Schrödinger equation into a set of Schrödinger equations for states, for electronic states for each electron. So this is the Hamiltonian, the kinetic energy of electron, the external potential that includes the interaction, so the potential from the nuclei and maybe some external fields, the electron repulsion in this Hartree potential, and the exchange correlation potential. So these functions, psi I, are unknown functions. They are one electron wave functions. And in order to solve this equation, we express these unknown functions as a linear combinations of some known functions, which are called the basis functions. And after doing so, after substituting this expansion into the Schrödinger equations, into these Kohn-Sham equations, we obtain an eigenvalue problem, which is a nonlinear problem because the matrix here depends actually on the eigenvectors themselves, so it has to be solved self-consistently. Now, if we think about this problem, so this is an eigenvalue problem, we have to diagonalize this Hamiltonian matrix. But the question is, for how many basis functions, what size of basis functions, which depends on the number of electrons in the system, we can actually do this for. So if we calculate the size of the matrix, we will find that maybe we can treat in reasonable time like maybe 10,000 or 50,000 electrons, but then it becomes a computational problem. However, if we count the electrons in 1 cubic millimeter of copper, for example, then we will see that it's about 10 to the 20th power of electrons. So the question is, how can we diagonalize such a matrix? It turns out that there is a very nice property of solids, which is so-called translational symmetry. Namely, for example, if I take a perfect crystal of copper, then every position of every atom in the bulk of the copper can be obtained from a position of a single atom by repeating this atom along so-called lattice vectors, primitive lattice vectors, A1, A2, A3. And this linear combination of this primitive lattice vectors with integer coefficients is just called a lattice vector. So just to introduce some concepts, let's consider a simplified case, the two-dimensional lattice, which is called Bravais lattice. So let's say we have an atom or a group of atoms located here, and then in this periodic solid, in this lattice, we obtain position of all atoms in the infinite space by a linear combination of these lattice vectors. For example, position of this atom is 3A2 minus 2A1, right? So we can obtain a position of every atom. So we can introduce a so-called unit cell, primitive unit cell, which is, in principle, has an arbitrary shape, but it has to satisfy two conditions. First, so when we repeat these unit cells, this shape in the whole space, there should be no unaccounted space, and these shapes should not overlap. Otherwise, the form is arbitrary. So how can we describe electronic structure of such a system, of an infinite system with infinite number of atoms? There are several ways to actually introduce the electronic structure of solids. One is more physical, more physicist way, is through uniform electron gas. But there is also another way suggested by Roald Hoffman, which is kind of combines the physics and chemistry, and so I chose this way. So let's say we have an atom that can form two bonds with other atoms, and now if we form a molecule, we will have a bonding state and anti-bonding state, right? Then we add another atom to make such a ring. Then we add some states here, and if we continue to do this, the electronic structure of the systems, when we have an infinite number of atoms in this ring, we will see that these electronic states will fill a whole band of states. A whole region of energy is filled with states, and these states are different by the number of nodes in this bonding between the atoms, so in this molecular orbitals. So this is called an electronic band, and we can see that, for example, the density of states varies as a function of energy here, right? There are more states here, less states there. But if we have an infinite number there, then the whole range of energies is filled with states. Another way to look at it, let's consider a molecule, for example. There is a bonding orbital, an anti-bonding orbital. And then if I bring more molecules like this into a chain, so if I bring another molecule, these bonding and anti-bonding orbitals will overlap, and they form more states. So, and if I continue to add molecules, I will fill a whole range of states here, a whole range of states here, and there will be some region of energies when there are no states. This is called the band gap. So, we have an infinite number of atoms in the system, right? But it's periodic, and this allows us actually to treat such a problem. And the first step in this direction is the Bloch's theorem. So our system is periodic, which means that it has this nice property that the potential, if I choose a point in space and I calculate potential in that point that acts on electrons, and then I take another point which is shifted by the lattice vector from that point, then I get the same potential. So this potential is periodic. And then the Bloch's theorem states that the wave function is not periodic with the same periodicity as the lattice, but it changes under such operation, translational operation, only by a phase factor. And the phase is k times r, where k is a k vector, is a vector in reciprocal space. So reciprocal space is simply calculated like this. So these vectors are vector products of the primitive lattice vectors, and they have this property that each reciprocal lattice vector is perpendicular to a pair of the normal lattice vectors in real space. So this is an example. So we have this, for example, lattice here, and then this would be our reciprocal space, and this k point lives in this reciprocal space. As a consequence of this expression, one can show that actually the wave function is then expressed like this, where here instead of the lattice vector I have now just a normal vector, and u of r is a periodic function. So what is the meaning? This k vector, it has actually a meaning, and we can see this from this very simple example. So we have, let's say we have a set of hydrogen atoms, a chain of hydrogen atoms, and then the wave function is expressed like this. So there are some phase vectors which depends on the k point and the position of the atom, and the 1s orbital on each atom. And if k equals 0, then all these 1s orbitals are combined constructively, so they overlap and make a fully bonding orbital. But if k is equal, for example, pi over a, then we will have this alternating sign, so minus plus minus plus. So it's completely anti-bonding orbital. So this k, it actually is a symmetry label for our electronic states and a node counter. So it shows how many nodes the wave function has, and as a consequence, it also, since the wave function should change sign here, so here the curvature of this wave function change would be higher, and this means a higher momentum, electron momentum. So this is the meaning of k. So far, there is no simplification, right? We just see that the wave functions can be represented in a nice way, some phase times the latest periodic function. But we still have an infinite number of states and an infinite number of k points. Well, the first step, the first simplification comes actually from the Bloch theorem. There is another consequence. So again, we have this wave function that is labeled by 4 indices. One is called the band index, which is discrete, n. And there is also 3 components of the k vector, which in principle is continuous. Each of these components is continuous. According to the Bloch theorem, we have this expression for the wave function where u and k is a lattice periodic function. Now, let's consider a lattice vector, a reciprocal lattice vector, which is a linear combination with the integer coefficients of the reciprocal lattice vectors. Then, if we consider a wave function at k point k plus g, this vector, then by easy transformation, we can see that it actually should correspond to a wave function, to a wave function maybe so with a different band index, but the same k point. So this means that in principle, we do not have to consider the whole k space. We can just consider one unit cell in the reciprocal space to describe the electronic structure of the system. So this unit cell in the reciprocal space is called a Brillouin zone. And so, as I mentioned before, the choice of the unit cell is in principle arbitrary. By convention, for this Brillouin zone, for the reciprocal space, a so-called Wigner-Seitz cell is chosen. So, because it's very easy to construct, and it satisfies all the conditions for the unit cell, namely, if you repeat it periodically, there is no empty space and there is no overlaps. So it's constructed in the following way. You take a point in the reciprocal unit cell, connected to its images in the neighboring unit cells, and then cut the connecting lines in the middle perpendicular with a plane. And these planes will cross each other and form a shape in this 3-dimensional reciprocal space, which satisfies the conditions for the unit cell. So this is called a Wigner-Seitz cell. For example, for a square lattice, the Wigner-Seitz cells would be like this. You can see these vectors connecting the images of the point, and then in this case, in 2-dimensional, these are not planes, but just the lines, right? And they form this shape. And for example, for this hexagonal lattice, this would be a Wigner-Seitz cell. In 3 dimensions, it's a bit more complicated. Here I show example of 2 most common lattices for elemental solids, the face-centered cubic and the body-centered cubic, FCC and BCC, where in a face-centered cubic, we have atoms in the corner of the cube and then atoms in the faces. And in the body-centered, we have, in addition to atoms in the corner, just one atom in the center of the cube. So we can construct the Wigner-Seitz cells for these lattices. So this is the Wigner-Seitz cell for this lattice, and this is the Wigner-Seitz cell for this lattice. Now, but we need in order to see what is the brilliant zone, we need to construct a reciprocal lattice. And it turns out that these two lattices are reciprocal of each other, actually. So if you construct a brilliant zone, a lattice, a unit cell in the reciprocal space for the FCC, this will be a Wigner-Seitz cells in the BCC lattice, right? And vice versa. So this is the brilliant zone for this lattice, and this is the brilliant zone for this lattice. So there is another property of this electronic structure of periodic solids, which is called time reversal symmetry. So usually in our problems that we consider in electronic structure problems, the Hamiltonian is Hermitian, and this means that the eigenstates, the eigenvalues, can be chosen to be real. And under such conditions, if I write the Schrödinger equation and then take a complex transform of this, I will obtain this equation, which means that psi star, the complex conjugate of psi and k, is actually a solution of the same Schrödinger equation with the same energy. And from the Bloch's theorem, we can actually see that this psi and k star behaves as psi and k, but with minus k. So this means that psi and k and psi and minus k are degenerate, and this is what is called the time reversal symmetry. So there's degeneracy of this kind, and which can be broken in case if we have a magnetic field. As I mentioned before, and as you heard in previous lectures, these wave functions we have to find, and we don't know their form. So what we do, we introduce functions of known form and make a linear combination out of them. There are many different choices for basis sets, and the point is that there is no universally good choice. Therefore, all different kinds of basis sets are used in different codes. A very popular and very powerful basis set for solid state problems is the plane wave basis set, which is simply has this form. And you can already see, so it resembles the Bloch's theorem, right? We have this periodic repeat. This basis set is completely delocalized, with perfectly fine for three-dimensional solid. It allows for analytic integrals to obtain the Hamiltonian matrix and other integrals. However, if you have, if you consider core electrons, which are very, so the core wave functions change very rapidly near the core, and therefore one would need a lot of these basis functions to represent these electrons. But this problem is solved by introducing pseudo potentials or a combination of plane waves with localized bases, and this will be discussed in the next lectures. Another popular choice of basis functions are Gaussians that are localized, so they are most suited for molecules, clusters, but also can be used for solids. And their advantage is that they also allow for analytic integrals, analytic calculation of integrals. So another choice is Slater-type orbitals, which has a slightly different form, right? There is a square here, no square there, and the exponent. They have an advantage, so they are also localized, but they have an advantage compared to Gaussians, that they describe correctly the cusp behavior of the wave function at the core, at the nucleus. And in theory, this would allow smaller number of such basis functions to describe the electronic structure. Finally, as we use in the FHI aims, we use the numeric atomic orbitals, which are localized, and their advantage is that they are very flexible. So there is a hope that we can find such a compact basis function, basis set, which is still very accurate. And there are other approaches, as was mentioned before, like wavelets or grid-based codes. Yes?
Can I ask a question like the last slide?
Before? Yeah, sure.
So in this case, the time reversal symmetry is valid for all the solids ejectors?
Yes, unless you have a magnetic field.
Okay, so if we can analyze a band structure like that, so all the band structure will have a time reversal symmetry.
Yes, yes. So how can we use localized basis sets to describe basis functions to describe a solid? Actually, no problem. One way to do it, this is how we do it in FHI aims, for example, is to introduce periodic basis functions that satisfy the Bloch's theorem. So we just introduce this basis function, which is linear combination of the normal basis functions, phi p, but we take into account the periodic repeats of these functions with a phase vector. It's a very simple exercise to check that these functions satisfy the Bloch's theorem. So this means that a linear combination of them would satisfy Bloch's theorem. That's what we need. So you can view these basis functions as a linear combination of these functions modulated by a plane wave here. So that's how we do it in FHI aims. Now, if we substitute this expression for the wave function into the Schrödinger equation, we obtain again the eigenvalue problem. In these matrices, the only difference is that we have this lattice sum here. But because these functions are localized, this sum truncates very rapidly. So there is no problem. And we have this eigenvalue problem for each k point. In practice, what we do not, so for this we would have to consider the whole space and then find all basis functions that overlap with basis functions in the main unit cell, in the original unit cell. But what we do, we actually fold in both the integration points and the pieces of the functions that overlap with the first unit cell into this first unit cell, and then take this kind of integrals. So again, if we have a periodic system, we fill a whole band with electronic states, and then we can look at the dependence of the energy of electronic states on this value of k. And if we plot this, we will find a curve something like this in the one-dimensional case, if we have only one-dimensional reciprocal space. So in each k point, so there is an infinite number of k points. In each k point, we have a different electronic state, which is can be occupied or empty, and they form such a band. So this dependence of energy on the k point is called dispersion. So again, for a periodic infinite crystal, there is an infinite number of states for each band index, differing by the k point. Here is an example for three-dimensional case. In three-dimensional case, this energy is a function of three components of the k vector. So it cannot be just represented as conveniently as here. But what is done by convention, actually, we take the Brillouin zone of this three-dimensional crystal, and then we choose a path in this Brillouin zone, and we go along this path and calculate these bends, the electronic states, along this path. So it is still one-dimensional. We kind of unfold this three-dimensional function into using this convention. And this path is chosen such that these lines connect important points in the Brillouin zone, which are symmetry points. Here is an example of aluminum band structure. So this is called the band structure, what we obtain after this procedure. And this is calculated with PV functional. So you can see this complex electronic structure that's so why this is chosen, why we choose this path to connect symmetry points is because symmetry points are points where something important and interesting usually happens, like some degeneracy lifting or degeneracy happens or other properties. And by convention, these energies are measured also along this standard path in this Brillouin zone, and therefore can be compared with calculations and experiment can be compared. So the measurements can be done with, for example, angular resolved photoemission spectroscopy. So we have infinite number of states and infinite number of key points. How can we calculate this? For example, how can I calculate the density, which in principle is an integral over the Brillouin zone of this square of the wave functions? For this, I would need to know wave functions in every key point, but there is infinite number of them. So it turns out that these wave functions and the energies are relatively smooth functions of k points. And therefore, we can introduce a grid to approximately calculate this kind of integrals. So there are many different ways to introduce such grids. For example, we just, so the key point at 0, 0, 0, right, it's called the gamma point, and we could introduce a grid that is centered at the gamma point. Or there is another way, which was suggested by Monkhorst and Peck, is when it's still a regular grid in the k-space, but it avoids the borders of the Brillouin zone and the gamma point. Actually, what they showed is that such a choice allows for better interpolation of the calculated wave functions and energies, and therefore you need smaller number of key points in that case. So it was very important before and in early days of density functional theory calculations, because it was important to have small number of key points. Nowadays, we often just use the gamma-centered grids because, especially in the localized basis codes, the cost of calculating the key points is not so large. So, and the gamma point is also an important point in the Brillouin zone, so it's good to know exact quantities for that point. So this is for square lattice, and if you read the literature, you will see that the original procedure suggested by Monkhorst and Peck would break this symmetry in more complex lattices like hexagonal one, but then a fix for this was suggested, and also similar to Monkhorst-Peck grids, one can choose also grids in the hexagonal lattice. So after we introduce the grid, these integrals can be represented as sums, with some weights. So just to demonstrate, the meaning of this band structure, let's consider a simple example of hydrogen molecules oriented like this, vertically, and separated by a distance a between each other. And we have this infinite chain of such hydrogen molecules. At the distance, so if the unit cell size is 10 angstrom, the band structure will look like this. So, which means that there is no dispersion, right? It's clear. It's clear to understand from what I said before, right? So the orbitals on one molecule do not overlap with the orbitals on the other, and therefore, no matter in which phase I combine them, nothing changes. So there is no dispersion. Now I start to decrease this distance, and I start to see a little bit of dispersion in the unoccupied states. I forgot to mention, so this these occupied states are here. So we start to see this dispersion in unoccupied states, but no dispersion in the occupied ones. And this is again clear. These states come from a diffuse unoccupied orbitals that starts to overlap already at this distance. So that's why we start to see dispersion here. But the occupied states are still localized. They do not overlap yet. And you do not see any dispersion. Now when I continue to decrease the distance between the molecules, I start to see also dispersion in the occupied states. And there are several features of the band structure that are important, in particular the band gap. So the energy difference between the highest occupied state and the lowest unoccupied. In this case, this is an example of indirect band gap because the smallest energy difference occurs at different gamma points. So at different gamma points. The direct gap for each k point stays about the same in this case. And you can imagine that at some point when I bring the molecules too close, very close to each other, then the band gap will disappear. So one can actually construct or draw a band structure without actually calculating it. And this was again given by Roald Hoffman. Let's consider a chain of 4 coordinated platinum complexes. Platinum has d orbitals and also p orbitals. And if we look at the d orbitals, for example, let's consider a dz square orbital. This is its shape, so it's extended in the z direction. And in case of k equals 0, we have a full bonding overlap, right? So we have some point, some energy at k equals 0. But at k pi over a, we have completely anti-bonding orbital. So we have some energy here, and we connect it by this smooth line. Now for xz and yz orbitals, so we have an anti-bonding overlap at k equals 0, so some point here. But it becomes bonding at pi over a, but this overlap is smaller than in case of z squared. So the variation becomes smaller, and it's in this direction. And finally, for xy orbital, this overlap is very small. So the variation with k point should be also small. And again, it's bonding at k equals 0 and anti-bonding at k equals pi over a. So we have something like this. So we already have the d band of this system. And so we can kind of think about the electronic structure before calculating it, actually, using this kind of understanding. In general, the solids are distinguished in 3 different classes. One class are insulators, and examples are magnesium oxide, sodium chloride, or zinc oxide, which have a large band gap, large compared to thermal energy, right, to kT. Then there are semiconductors, such as silicon, germanium, or doped. It can be also doped insulators. And by this, we make them semiconductors. In which case, the band gap is comparable to kT. And in such a situation, at realistic conditions, if we have some finite temperature, the electrons can be thermally excited from the occupied states to the unoccupied ones. So this is the property of a semiconductor. And finally, in the 3rd class of materials, we have metals such as copper, aluminum, iron, in which the occupied and unoccupied bands are not separated. So we have partially occupied bands. Here is partially occupied band here and here, already at 0 temperature. This energy that separates occupied from unoccupied states is called Fermi energy. This is an important concept, the Fermi energy and the Fermi surface for understanding metal properties and physics. And it's defined like this. So it's a surface in the reciprocal space where the energy of states epsilon nk of Kohn-Sham states is equal to the Fermi energy. So this is an equation, right, for 3 variables, which means that it's a surface if we solve this equation in 3-dimensional space. For free electrons, we know what the shape of this surface should be. It's a sphere, right? Here is the equation. It's equation for a sphere. And if you look at the, by the way, so this band index, it forms different parts of this surface. Now, if we look at the Fermi surface of potassium, for example, it looks very close to the free electron case, right? So it's a very nice, close to spherical shape. So this is a system that can be approximated very well with a free electron model. But if we look at copper now, we start to see some deviations, and aluminum has a completely different electronic structure, right? There is, you can see here, there is a periodic table of Fermi surfaces, very beautiful. One important point is that to describe, so this is a surface in the reciprocal space, right? So it's a very sharp property. And in order to describe it correctly, we have to have a lot of K points. So we have to increase the density of K points to describe accurately this Fermi surface. And therefore, in general, for metals, one has to include more K points to converge the properties. So we saw that the band structure gives a lot of information about electronic structure of a solid, but in some cases it might be too much, right? We have the whole K dependence of the states, but if we just want to see the what is the band gap and what is the density of states, then we just plot that. So the density of states is simply a number of states within an energy unit per volume of a solid. So which is calculated like this. So this means that it has the units, right? States per energy unit per volume unit. And in practice, what we do to calculate, so we would have to take every state in the calculation at every K point and add them up, and we obtain the density of states. But in practice, of course, we do not have calculation at every K point, right? We just have a grid. And what we do, we replace this one with this integral of a delta function with a Gaussian. And so these Gaussians are added together, and we obtain something like this. You can see how density of states in a more compact way reflects properties of the band structure. So it gives the width of bands, it gives the band gap, and the density of states at different energies. One can get more chemical information about bonding in the solid by calculating projected density of states. The idea is, so it's again, we sum up, we count the number of states per energy interval per volume, but we actually calculate contribution for each state of a particular localized orbital. For example, a p orbital or a d orbital on a certain atom. What this allows to do, it allows to resolve this, this density of states into contributions of different orbitals on different atoms. So this is called the projected density of states. For example, in this case, we look at the band structure and density of states of magnesium oxide. And by calculating this projected density of states, we find that the top of the valence band here is mainly composed of the oxygen, top of the valence band here is composed of oxygen 2p states, while bottom of the conduction band is due to magnesium 3s mainly, right? So we can get this information, this kind of chemical information about the bonding in the solid. So it gives us this chemical interpretation in terms of orbitals, but there is a problem that in principle we do not know. So this localized orbitals, they are non-orthogonal, they can overlap with each other. So it's we have to resolve this ambiguity somehow, and therefore this is only a qualitative analysis tool. We have to resolve these ambiguities by truncating the integral in the space, in the this integral in the space, or by orthogonalizing this localized orbitals. One important quantity that we need to calculate in a periodic system is the electrostatic potential. So we have charged particles, electrons and nuclei. They interact with each other through Coulomb forces, and therefore it's important to be able to calculate this electrostatic potential. So let's consider an example. Let's say we have this system, like for example sodium chloride, where we have plus and minus ions, and we take a point near one of the atoms and calculate electrostatic potential from all atoms in the system. And we first choose this small part of the system and calculate potential, and then we increase the size and so on. And if you look carefully at this curve, we see that it converges extremely slowly. After including a million of point charges, there is still no sign of convergence. This is how we calculate this potential. So this would mean that every time when we need to calculate the electrostatic potential, this would take a lot of effort, actually. Of course, it's a simple calculation. It's just the charges, right? But still, it's not converged yet. We would need more charges, and it would take too much time. And the accuracy would be questionable still. There is a trick, however, which allows to solve this problem and calculate exactly the electrostatic potential of the whole infinite array of charges. This is called Ewald method, or Ewald summation method. The idea is that, so here we have a point charge. So the potential is a combination of Coulomb potentials from point charge at different points and periodic in different unit cells. What we can do is we screen this charge with a Gaussian, with some Gaussian charge distribution. And, but then we add another charge distribution with the same Gaussian but opposite sign. So if we now calculate potential from this part, it will be actually very localized in space. But this part, of course, we still have to deal with. But it turns out, so this is still long range. But it turns out that we can treat this part in a reciprocal space. We can simply get a Fourier transform of this and calculate for the infinite space, because this function is smooth, contrary to a point charge. And so we calculate this in the real space. So the potential for this kind of charge density can be calculated analytically, and we have it here. And it converges, if you look carefully here, very fast with the distance to the charge, with the distance to the point in which we calculate the potential. And this converges very fast in a reciprocal space here. There is a parameter, eta, but in principle there is a good choice universally for all systems. So this decays very fast with the size of the reciprocal lattice vector. If we look here, at g equals 0, this term diverges, right? So this would mean that if I have a charge in the unit cell, which is not compensated, its energy would be infinite of such system. The energy of the array of charges which are not compensated is infinite. But if you look carefully, if the system is neutral, then actually sum of charges is 0, then this g equals 0 term disappears. So so it's very nice. We solve the problem of calculating electrostatic potential of an infinite system. One problem that appears after doing this is that in a solid we do not have a universal potential energy reference. Yeah, we do not have, for example, a vacuum level like for a cluster molecule or even a surface. In a three-dimensional solid, we don't have that. And therefore, it's important to remember when you compare energies of systems with different charges per unit cell. I forgot to mention, so you can still calculate the charged unit cell, so for example, in WASP or an FHI AIMS, you can specify, I want a charge per unit cell, right? And you will not get an infinite energy. So what happens? What happens is that we introduce, so implicitly, by just omitting this G equals 0 term, we introduce a uniform compensating background charge. So we compensate the charge, and that's why we can calculate energy. But this can shift the potential reference, and therefore comparing unit cells with different charge should be done carefully. So how can we use this kind of approaches to calculate periodic system to model non-periodic cases, in particular surfaces, defects, and so on? It turns out that this can be done, and the approach is called the supercell approach. So, for example, for a surface, let's say we cut a solid at a certain plane, by a certain plane, right? And then we split the two parts and introduce a unit cell that now contains a bit of vacuum, right? So now if we periodically repeat it, we get the system, we get a surface, actually a slab, right, with two surfaces, which is periodically repeated in this direction normal to the surface. But this is a three-dimensional periodic system formally, but we model a surface now with this approach. So this approach allows to account for lateral periodicity, which is very nice. So we have a robust boundary conditions in the plane of the surface. But we have to worry about several things. In particular, the vacuum region should be sufficiently broad to decouple one surface from the other, from the image, right? Different basis sets react differently to this kind of problem. So, for example, the localized basis sets allow to use larger vacuum region without too much effort. But in plane waves, the cost of calculation grows with the vacuum size. But in all cases, you of course can find some golden middle where the size of the vacuum is large enough. But this should be always tested in calculations. The second problem is the slab thickness, right? If we want to model just one surface of the solid, we do not have to remember that we have to remember that in our model we have the second surface, right? And these two surfaces can interact, so we have to make sure that the slab thickness is big enough. For semiconductors, this problem can be addressed by saturating the dangling bonds at one of the surfaces to mimic the environment of those atoms at the surface such that it becomes close to the bulk environment. If we have some non-equivalent surfaces, for example, we adsorb some species here, or we have a system without center of symmetry, then we can get a dipole moment per unit cell in the system, which is directed along this z direction. And in that case, actually, in order to make the system periodic, we implicitly introduce an artificial electric field that makes the potential periodic for such systems. And so one has to kind of compensate this electric field to remove its spurious effects. And this can be done with a dipole correction. An alternative to modeling non-periodic systems such as surfaces or defects would be to use cluster models. So one can also use this, but one has to make sure that the boundary conditions are correctly modeled, right? Correctly described.
Sorry, what do you mean by boundary conditions on clusters?
Huh?
What do you mean by boundary conditions on clusters?
Sorry, I meant embedded clusters, of course. So if we want to model a surface with a cluster, we have to embed it to mimic the potential of the missing atoms at that region of the cluster. So for surfaces, for the bulk, as I showed, we can calculate the band structure. For surfaces, we can actually do even more. Because, of course, if we take the slab model and calculate the band structure, we see a lot of states. But we don't know which one of them are due to surface or bulk and so on. But there is a way to actually construct a surface band structure, which allows to distinguish between surface states and bulk states from such calculations. So the idea is that for the surface, of course, our Brillouin zone is two-dimensional, right? Because in one dimension, we have a very long vector. Theoretically, it should be infinite. And so this means that the Brillouin zone in the corresponding reciprocal direction should be 0. So it's a two-dimensional Brillouin zone for the surface. And in order to separate surface states from the bulk states, what we can do is we take a unit cell of the bulk such that the surface Brillouin zone can be obtained simply by reducing the size along the kz vector of this Brillouin zone in the bulk. And then we calculate the bulk electronic structure at different k points along the kz direction and the bulk, right? In this way, we obtain a whole range of energies which are filled with bands from the bulk. But and then we do the surface calculation. And what we obtain is something like this. So there are energies, so there are regions of energies that are filled with bulk bands, but then there are surface states which appear in the in the regions where there is no bulk states, right? And so these surface states, there can be two different types of surface states, Shockley surface states and Thumb surface states. By the way, this is a surface band structure of copper 111. So the Shockley surface states have this characteristic. So they have this form. It's kind of scattering of the electrons from in the bulk from the surface. They continue into the bulk infinitely, but they still kind of decay from the surface into the bulk. And this is because the potential periodicity is broken at the surface. So these are Shockley surface states. Actually, such decaying states can be treated as block states with complex k vector. And this can be also done, and there is a lot of literature about this. But this makes the picture of the electronic structure even more complex. And there is a Thumb surface states, which can be understood as dangling bonds. So if I have a periodic system and then I create a surface, so here I just use a one-dimensional system to model this, then at the ends of this chain we would have dangling states which have different environment, and they would enter the gap of the system. As an example of how this concept of surface band structure can be used, I give this example of silicon surface reconstruction 2x1 dimerization at the 001 surface of silicon. So if we cut the bulk of silicon along this 001 direction, then at the surface we have these atoms which, because we have unsaturated bonds, they can come close to each other and form bonds between themselves, a pi bond here. So this is called dimer reconstruction. Here is the side view. However, the symmetry of this dimer can be broken, and in fact, there was a discussion in literature whether this really happens and how can one actually prove it experimentally. So here you have a symmetric dimer bonding structure. So you have sp3 hybrids that form a kind of pi bond and pi anti-bond. And then if you have a broken symmetry dimer, then the upper atom becomes more S-like orbital, which is filled, and there is a partial charge transfer from the down atom to that atom. So the symmetry is broken, and if we calculate the surface electronic structure, the surface band structure, then we get two cases, the symmetric dimer and the asymmetric dimer reconstruction. And we can see that, so if we try to compare the symmetric dimer model to experiment, it does not fit very well. But if we actually use asymmetric model, then the fit to this measured results with photoemission spectroscopy is actually much better. So by comparing these results, we can conclude that there is a dimer reconstruction at the surface. So in conclusion, I have shown that periodic models can be efficiently used to study concentration and coverage dependencies by molecules or defects, including also infinitely dilute limit by using the supercells, right? There is a lot of useful and experimentally testable information on materials' properties that can be obtained from analysis of its electronic structure, such as band structure, density of states, atom projected density of states. And as you will learn, as you already learned and will learn further, that there is still a lot of development that we need to do to accurately calculate the electronic structure of solids. And here you can see some literature, and thank you for your attention.